Welcome to the class. Myself Professor D.S. Rai, Professor Department of Civil Engineering, BBD ITM Lucknow. We will discuss here a subject KCE 602, lecture number 30, in which we will discuss design of flexible pavement by CBR method IRC 37 2018. The reference books are Highway Engineering by Khanna and Jesto, Principle of Transportation Engineering by Partho Chakravarti and Imesh Das, Pavement Design by R. Srinivas Kumar, and Building Materials by Dr. S.K. Duggal. The content of today's topic is design of flexible pavement based on IRC 37 2012, traffic, lane distribution factors, vehicle damage factors, effective CBR, catalogues and illustrations. So, we will discuss here one by one. The design of flexible pavement is based on IRC 37 2012. It is also called CBR method. IRC has published a new code of IRC 37 in 2018, but it is more or less based on the software based. So, IRC has published IRC 37 in 2012, it is also called CBR method. So, we will discuss here the CBR method by which we can design a pavement thickness. So, here the load is transfer is based on layer system and grain to grain. Pavement system is flexible and have no or very less flexural strength. Based on CBR value of subgrade, magnitude of wheel load, intensity of traffic load. For the purpose of guidelines, flexible pavements includes pavement with bituminous surfacing over granular base and granular sub base, cementitious bases and sub bases with a crack relief layer of aggregate interlayer below the bituminous surfacing. Cementitious base and sub base with SAMI in between bituminous surfacing and cementitious base layer for retarding the reflection cracks into the bituminous layer. The next is reclaimed asphalt pavement wrap with or without addition of fresh aggregate treated with foamed bitumen or bitumen emulsion. The use of deep strength long life bituminous pavement. So, these are the various treatment if there are existing pavement. Now, come to the first parameter, that is a traffic. The design traffic in terms of cumulative number of center axle to be carried during the design life of the road should computed using the following equation. We have discussed in previous lecture that if a vehicle is going on a highway, even have a more load, there will no any problems. But when there is a repetition of load, then there will be a fatigue failures. So, for designing of pavement thickness, the critical condition is fatigue failure, to take care of fatigue failures. So, for the traffic we have to go for the designing the number of cumulative number of standard axle. So, the formula that is used to calculate the MSA, million standard axle, that is by n is equal to 365 1 plus r to the power n minus 1 divided by r multiplied by A multiplied by D multiplied by F, where n is cumulative number of standard axles to be catered for in design in terms of MSA, million standard axle. A is the initial traffic in the year of completion of construction in terms of number of commercial vehicle per day. So, here A will be equal to P 1 plus r to the power x. Here P is the number of commercial vehicle as per last count, x the number of years between the last count and the year of completion of the construction, and n is design life in years. We generally take NH and SH for a minimum life period of 15 years. For expressway and urban roads, take the design life for 20 years, and for other category of road, design life has been taken as 10 to 15 years. One term is important, this is A, the initial traffic. Suppose the last count of traffic has been done. Suppose we are preparing a project this time and last count was done 2 years back, and suppose the project will be completed in 3 years. So, here from last count to the year of completion, that will be the 5 years, is it. So, A will be calculated as P. P is the initial traffic during last count, means 2 years back. So, here P is the last count, and x here is and R is the rate of growth of the traffic, because we have not done the traffic during this period. So, we will assume a certain growth rate for the calculation of the traffic. So, it is generally taken 5% per year. Earlier it was taken 7.5%, now IRC has now reduced 5%. So, A could be calculated at the time of completion of the project, completion of the road. So, by this method we can calculate the value of A. So, on the basis of these all data, we have our growth rate, and here we take growth rate is 0.5%, 5%, sorry, 5%. R is the growth rate that we will take 5%. Now, come to A, we have already discussed. Now, next is D. D is the lane distribution factor. So, for the single lane road, the traffic tends to more channelize on a single lane road than 2 lane roads, and to allow for this concentration of wheel load repetition, the design should be based on the total number of commercial vehicles in both directions. So, for the single lane road, we will take the total number of commercial vehicles. Then come to the 2-lane single carriageway. The design should be based on 50% of the total number of commercial vehicles in both directions. If vehicle damage factor is in one direction is higher, the traffic in the direction of higher VCD is recommended for design. 4-lane single carriageway. The design should be based on the 40% of the total number of the commercial vehicle in the both direction. For the dual carriageway, the design of dual 2-lane carriage roads should be based on 75% of the total number of commercial vehicles. So, this is all about the lane distribution factors, means how much effective load is coming on the road, that will be decided by the lane distribution factor. The next parameter is F. F is the vehicle damage factor. The vehicle damage factor is a multiplier. To convert the number of commercial vehicles of different axle load and the axle configuration into the number of repetition of a standard axle load of magnitude 80 kilonewton. It is defined as equivalent number of a standard axle per commercial vehicle. So, the equation for computing the equivalency factor for the single axle with the single wheel on either side. This is the one axle and this is the. So, this is a single axle and single wheel on either side. So, for this one single wheel with the single axle with the single wheel on either side, the factor will be axle load in kilonewton. Axle load in kilonewton divided by 65 to the power 4. That will give the equivalency factor. Suppose single axle with the dual wheels on either side. Dual wheel on either side in single axle. So, the equivalency factor will be axle load in kilonewton divided by 80 to the power 4. Now, tandem axle means if there is a 2 axle having 2 wheels on the either side, the equivalency factor will be axle load in kilonewton divided by 148 to the power 4. Then the tandem axle with the dual wheel on either side, the axle load in kilonewton divided by 224 to the power 4. So, by this method we can calculate the equivalency factor for the VDF. So, suppose there is no availability of data. In that case, IRC has recommended the indicative VDF value, and these values are, if data is not available, then we can take this value as a VDF. See here, when the commercial vehicle lies between 0 to 150. In that case, the VDF will be in rolling and plane 1.5 and hilly area 0.5. Between 150 to 1500, the VDF will be 3.5 in the rolling and plain area and 1.5 in the hilly region. And if commercial vehicle is more than 1500, then the VDF will be taken as 4.5 in plain or rolling areas and 2.5 in the hilly region. So, in absence of the data, we can use these data that have been given by the IRC in IRC 37. Now, come to the subgrade. This is the another important parameter for designing the pavement thickness. The subgrade is the top 500 mm of the embankment immediately below the bottom of the pavement and is made of in situ material or select soil. The in situ material CBR of subgrade soil can be determined from the dynamic cone penetration test having cone 60 degree, and the formula used for calculating the CBR log base 10 CBR will be equal to 2.465 minus 1.12 log base 10 n. N is the number of blows. So, by this method we can calculate the CBR of soil. Now, come to the effective CBR, where there is a significant difference between the CBR of the select subgrade and embankment soil. The design should be based on the effective CBR, and that could be calculated by this chart. The effective CBR of the subgrade can be determined by, see, on the x axis this is the CBR of the soil and this is the effective CBR of the subgrade. So, by this method we can calculate, if necessary, then we can extend it, and by this method, suppose here is a 7, the effective CBR will be say 16, 17. So, effective CBR could be calculated by this chart and that could be used. So, and now the IRC has recommended that no soil should be used as a subgrade having effective CBR less than 8. So, we have to select a soil having CBR more than 8 effective CBR. Effective CBR should be like between the CBR of the original soil and the CBR of the select soil. So, by this chart the effective CBR lies between the CBR of the select soil and CBR of the in situ soil. Now, come to the design, the pavement design parameter. First we have discussed effective CBR, then we have already discussed N, the cumulative number of standard axles in median standard axle, that is MSA. It is a MSA. Now, IRC has prepared a design thickness of pavement in design catalog in IRC 37 2012 with the CBR ranging from 3% to 15%, means catalog prepared by IRC having effective CBR ranging from 3 to 15% and MSA ranging from 2 to 150, 2 to 150 MSA. In design catalog, material composition like a granular subbase, granular base, dense bituminous macadam, bituminous concrete and semi-dense bituminous concrete thickness are also given in the catalog. So, it is a ready reckoner. Just calculate the MSA and effective CBR, then choosing the correct catalog, and we can get the thickness of each layer of the flexible pavement. SDBC has been provided up to traffic 5 MSA. Suppose the traffic producing 5 MSA means million standard axle. In that case, we can use SDBC, semi dense bituminous concrete, as a wearing surface. BC has been provided for the traffic 5 MSA to 150 MSA. If the traffic lies between 5 MSA to 150 MSA, then we have to choose BC, bituminous concrete, as a wearing surface. So, see here, this is a catalog, and I have just choose a plate number 7 having CBR 9 to 10%, and this is the MSA 2, 5, 10, 20, 30, 50, 100 and 150. This is the MSA, means traffic in the cumulative number, and on y axis the pavement thickness is given in millimeter. So, here suppose a soil having MSA of 10, then we can choose this catalog, in which 200 has been given to the sub base, 250 base course, 50 dBm and 40 BC, because here MSA is more than 5. So, we can take BC as a wearing surface. If the calculated MSA lies between 2 MSA, suppose here our MSA lies between say 30, between 20 and 30, so 25. So, lies between 2 MSA plate, the higher MSA has been selected for the design purpose. So, we will design on the basis of 30 MSA. For the traffic more than 30 MSA, VG 40 between is recommended for the BC and DBM, is it? And coarse graded GSB with the fines less than 2% may also be used. So, this is the way we can design. So, I have just given an illustration, and that has been taken from the code IRC 37/2012. Say this is the 4-lane divided carriageway, this is the data. Example is design of pavement construction of a new flexible pavement with the following data 4-lane divided carriageway, initial traffic is given 5000 VC per day in both directions. The growth rate has been given as a 6%, design life is 20 years, vehicle damage factor 5.2 based on the axle load survey, CBR of the soil below 500 mm subgrade is 3%, CBR of 500 mm of the subgrade from the borrow pit means select soil 10%. So, the now calculation lane distribution factor will be 75, because there are 2 lanes. Initial traffic is 2500 CVD, assuming 50% in each direction. Vacuole dimension VDF is given 5.2. The cumulative number of standard axle can be calculated by this formula, n is equal to 365 1 plus r to the power n minus 1 by r into A into D into F. So, here given r is equal to 6%, n is equal to 20 years, initial traffic 5000 for the 4 lanes. So, A will be 25 VCD, D will be 0.75 and F is given 5.2. So, we can calculate the value of n, that will come 131 MSA. So, we can choose 131 MSA lies here, somewhere here. So, as per norms, we will take 150 MSA for the design purpose, and here it is given 230 sub base, 250 base, 140 dBm and 50 BC. So, by just choosing the from the catalog, we can calculate the thickness of each layers and compositions. So, the CBR of embankment material 3%, CBR of 500 mm of subgrade, so 10%. The effective CBR from the chart 5.1, that will be 7%. The thickness of granular layer GSB will be 230 mm, WMM 250 mm, thickness of proposed bituminous layer with VG40 bitumen DBM 140 mm and BC bituminous concrete for the wearing surface 50 mm. So, the total thickness will come 230 plus 250 plus 140 plus 50. So, that will come 670 mm. So, by this method we can easily calculate the entire thickness of the pavement. So, this is the end and thank you very much.